it's defined as that figure, then it's equal to 1 plus 1 over n when n is a large number, and that whole figure, all that inside the parentheses, is raised to the n power. We can never take n all the way up to infinity, but as we make it larger and larger, we get better and better approximations for e. It's easy to make that big enough for any accuracy we actually need. Now, you will probably have already noticed that that definition for E has a lot in common. It looks very similar to the standard form of the compound interest formula that we've been using. That formula has an advantage that we sort of understand the parts, and we've been through where that formula came from. The formula for E seems almost to fit in there, to be the parenthesis raised to a power, but not quite. And we wonder, well, there's that R in place of number 1, R for rate in the compound interest formula, where there's a simple easy number 1 in the definition of E. And there's a compound power, not just n, but n times t, a number of years. So it's not quite the same, but it's not completely different either. So that's a kind of intellectual problem we face. How can we make use of E? How can we substitute? And we'll try to handle that problem later. But compare the two formulas. The one there at the bottom then is the continuous compounding formula. It will give you an accurate number when n is very large. And the first thing to notice is to go back to the promise I made at the beginning. The formula at the bottom is simpler. It takes out a few steps. And it seems to reduce things to what we know, or the easiest of the unknowns. We're interested in problems involving a P naught, an initial principle, whatever a population is at the beginning, or whatever money you lay down at the start of an investment, a PT, what the principle is at the end, that some future time that you're interested in. Those are there prominently in that bottom formula. And then we have a rate in a number of years. And it seems like everything in that formula is only the things that we want to know and calculate with, except for the number E, which is not something that should cause us any problems because we know it's a definite amount and our calculators are already set up to let us handle that. So let's consider the question of why would we want to switch from the top to the bottom? And the general answer, why would we want to use that bottom formula rather than the top one? And the general answer is, well, it's more accurate when we're dealing with natural problems. That is, the problem of continuous compounding is a natural problem. Things that grow don't know anything about our weeks or months or hours. They just grow as they grow. So more accurate, but also simpler to deal with, fewer parts. And it's easier to call any one of those variables the unknown. And with the help of the others being known, to solve for x, and to find out the unknown given our knowns. So in order to see how that works, why that's the case, let's go to a standard problem of compound interest of the kind we've been dealing with. So I've just arbitrarily set one up. There are the two formula at the top, and we're imagining we've got some investment that perhaps takes $200. We want to know what the investment is going to be after 7 years at a 3% annual rate of growth. And our way of doing this so far has simply been to plug all those knowns into the compound interest formula so that it will produce P sub t, the future value. So just to go on plugging the way we do, if we have a value for the initial investment, then we put that where it belongs in the formula at the bottom. We've decided that our unknown is the future value, so I'll put an x in its place in the formula to represent the unknown in the standard way. There's my rate, translated from a percentage to a regular decimal. There's my time, 7 years, and then all I need is some compounding period. I'll pick daily because we want a large number. We can approximate 360 days in a year. That's easier to deal with and good enough for our purposes. And now this formula will produce an answer. It takes some tapping on the calculator, but the calculator does the really hard work. That's what we have. That rate for that time with that initial principal gives you a future value of $246.73. Now, if that's what we wanted to do, we wouldn't have to bother with the E. Sometimes it's better to stick with what you know. We could simply keep on doing with this, but let's suppose we change our unknown. Suppose I'm interested in when my investment would double, or actually, as I've set it up, not so much when, as what kind of rate would I need in order for my investment to double in that time? So let's suppose I know the future value, but I have a different question. What rate do I need? So I'll put in the future value that I've decided I know in place of our old x, and I'll create a new x where I had r before, where I had the rate. And now it seems that it's going to be difficult in order to solve for x in this situation. Not that we couldn't do it, not that I doubt you all. I bet we could produce an answer, but it doesn't seem easy. But let's conceive this again differently as a problem of continual compounding. We'll use the other formula. It has this to recommend it, that it's more accurate in most natural situations. But also this, it's simpler. So I'll plug in what I know. I know the future value. I know the initial value. E is a constant, so I in my calculator have known that all along. The rate is where I put my x, because that's what I'm interested in, and the time I know. So if I've only got 7 years and I want to turn $200 into $400, what kind of an annual return do I have? Do I need? And this could be a problem for voting, or you're trying to market something. You're wondering whether certain trends will continue. How fast will people take up certain habits and hobbies? It could be a problem in biology or chemistry. But in order to solve it, if I'm using this continual interest formula, which is simpler, then it's not too difficult to recognize how to solve it. It might take you a little bit of time to figure that out, and maybe it would be worth it for you to pause the video and work it on your own, but I'll go through the steps. I can try to isolate my unknown by taking the 200 out of the right side of equation. I can do that by dividing both sides by 200. I get that fraction on the left side. Now I can reduce that to the number of 2, because we understand very well what that fraction 400 divided by 200 comes down to. So now I've got the number 2 is equal to e raised to some power. But then my calculator is all set up because it's got a natural log function to help me with that sort of problem. What power do you have to raise e to so that it produces e to that power is the number 2? Well, that's the question of what's the natural log of 2. I just said that over in a different way. My calculator will easily produce that it's 0.69. We could consider, does that seem reasonable? Well, we know that e to the 0 power is going to have to be 1 because any number to the 0 power will be 1. We could say that e to the first power is going to be 2.71, etc., because any number to the first power is itself. So I'm interested in this number 2, which is between 1 and the value of e, so I would expect that the natural log of 2 would be between 0 and 1, and a little closer to 1, and that's what I get, 0.69. And so now what have I come down to? I know that the number 2 is equal to e raised to the x times 7 power, but I don't know what x is, so I can't fill that out. But I have discovered through my calculator that e raised to the 0.69 power is approximately 2. So it looks as though I can move one step forward, one crucial step forward to understanding the value of x. If e to the 0.69 power and e to the x times 7 power both result in 2, then those two things, 0.69 and x times 7, must be equal. And now I've got the simplest kind of algebra problem that anyone would have to deal with. I can simply divide both sides of my equation by 7. That I get just a little less than 0.1, or I can say that I've solved my problem if I want to turn 200 into 400 in a period of 7 years. I'm going to need just a little bit less than a 10% annual yield to make that possible. So there is the formula for problems of continual compounding, and when you get used to this, you will see that solving problems is actually rather easy. The algebra is simple and straightforward, except for having that compound exponent. But once you get used to using natural logs, you will see that this is nothing to cause you any great difficulty. By a simple algebraic transformation, I can create this new formula, which will be useful for many different situations. Now, we all have good cause to remember that we're in a big problem of growth now, of continuous compounding now under the cloud of the coronavirus. And in some ways it's the perfect time to learn how to solve questions of this kind so that we go into the future a little better prepared with knowledge.